Okay, so like I said, there's lots of stuff going on in this section. I'm gonna try to break it down and simplify it the easiest or the best that I can. Whether that works or not, we'll see. But I'm gonna try my best to make it make sense. So the main thing of this section is this fundamental theorem of algebra. So what that says, so if p of x is a polynomial of degree n is greater than or equal to 1 with complex coefficients, that just means like numbers as coefficients, then p of x has at least one complex zero. So what they're saying there is if you've got any kind of polynomial, whether it's like, x squared or x to the third or something like that, as long as that power is greater than or equal to 1, you're going to have some zero, okay? Now, sometimes the zeros are actually going to show up on our graphs. Sometimes you're not going to be able to see where they actually cross because they're like those imaginary ones we were kind of talking about the other day. And I'll kind of show you some pictures of that in a second here. That next theorem then, or I think it's theorem, yeah, number of zeros of a polynomial. So it says a polynomial of degree n is greater than or equal to 1. So again, whatever your n is, as long as it's bigger than or equal to 1, with complex coefficients, has exactly n complex zeros if multiplicities are counted. So that's just saying whatever your degree of the polynomial is, that's how many zeros you're going to have. So if it's something like x to the third, that means you're going to have 3 zeros. Now what gets a little bit confusing is it says it has 3 zeros, but it might only cross the graph in one spot, okay? And that's when this multiplicity stuff comes into play, okay? I'm going to show you some pictures first, and then I'm going to talk more about the multiplicity stuff. In your packets, there's a little chart that's from the book. It's like after the 3 examples for the 7-6 stuff, but it's something kind of like this. These are just breaking down like quadratic ones here. So all of these are x to the squared, so they're all our U-shaped graphs. We've talked about this before, but typically when we're talking about the zeros, we're talking about where it's crossing this line, right? Where it's crossing that x-axis. So like in one like this, you can see right there, and right there it's crossing, so those would be our zeros, and they kind of show that here, right, where it's like the 2 and the 4. There's also situations where we just cross in one spot, so it's crossing right there at the 3. Now here, what's kind of the new thing to us is technically it's not crossing this line at all, but based on those theorems we just had, if this is a polynomial of some kind with, some power that's 1 or greater than or equal to 1, you have to have zeros here. What these are going to be called is they're like our complex ones or our non-real ones, because technically you have zeros here, they're just somewhere else on it. They're not necessarily crossing right there, okay? So these are going to be when it's like a complex zero, okay? And you can kind of see that here, how this one, see, it's like for your zeros, it's 3 minus I and then 3 plus I. Those are still your zeros, even though it doesn't actually theoretically cross that line, okay? So like in this case, you would have 2 real solutions. So if it's crossing like that, you would have 2 real answers, and real just means like not imaginary, so it doesn't have the I with it. In this case, you would have 1 real solution. And then in the last case, again, it doesn't actually cross the line, so you don't have any real answers, but this would be 2 non-real solutions. So again, it's not a 0 like we would typically think, but now we're getting to kind of some higher up level math stuff. We can actually find solutions there. They're just up further and not on that line, okay? Another important thing to note, and we'll talk about this in a little bit as well, when you have a situation like this where it is 2 non-real solutions, you can see there how they have i's. These values are always complex conjugates of each other. You remember writing that from the other day where it's basically, like, a plus bi or whatever. And then it's always opposite signs in the middle where the numbers and letters and stuff are all the same, but the sign switches. That we call complex conjugates. So I'm going to write that off to the side, complex conjugates, if I can spell conjugates right. And like I said, there's a theorem that you guys just wrote down that we'll talk about in a little bit that says if one of these is a 0, the complex conjugate is also a 0, okay? And it's because they're right across from each other. Does that relatively kind of make sense? Now, the new thing to us is this multiplicity business. So what the multiplicity is it's the number of times that whatever our factor is appears in the polynomial. Okay, so like if we have a situation like this where it's like, x plus 3 to the 4th and then x minus 2 to the 7th, here we would have two solutions. Okay, so our two zeros would be -3 and 2. Okay, remember how it's always you take whatever that chunk is and set it equal to 0. That's how they're getting it. So like if I had like x plus 3 and I set that equal to 0, we know it's like -3, -3, right? So that's how they're getting the x of -3. Now the new thing to us is this multiplicity stuff. So whatever this power is, that's always what the multiplicity is. Okay, so if this was like to the power 4, that means a multiplicity of 4. If it's the power of 7, that means it's a multiplicity of 7. Okay, that's kind of confusing, so let me kind of show you here on this. So in this situation, like this middle one here, our 0 is 3, but this 3 has a multiplicity of 2, so really there's only one answer, but technically it could happen twice, because if I look here, if this is x minus 3 times x minus 3, isn't that the same as x minus 3 squared? So couldn't that same answer technically happen twice? Does that make sense? So like I did actually do it out with quadratic. So you guys remember quadratic formula, right? So I solved this out with quadratic. What ends up happening here is if your discriminant, you guys remember discriminant from the other day where it's under that square root, if that value is a 0, when we go to add or subtract that 0, aren't we always going to kick out the same exact answer? Yeah, so technically we only have one 0 here, which is at 3, but it has a multiplicity of 2 because technically there was two different ways we could get to that. Does that kind of relatively make sense? And it's always the same as what the power is. So like here, it might not say it as that power, but you could rewrite it as that power. Okay. The other thing with the multiplicity stuff, I put this little packet thingy on Google Classroom or the website or somewhere. Don't worry too much about this, but this was kind of an interesting thing that I found when I was doing some of the research on the multiplicity stuff and why it's actually important. So all 4 of these graphs here actually all have the same exact 0 answers. Okay, so like here you can see, it's x plus 6, so that would have a 0 of -6. This is x minus 7, so that would have a 0 at 7, and you can see that crosses at 6, crosses at 7. But if I look at every single one of those graphs, are those graphs even remotely the same as each other? Not really, right? But they all technically have the same zeros, so this is where the multiplicity stuff is important because it kind of helps you determine what the shape of the graph is going to be. Because technically all of our answers here are -6 and 7 for the zeros, but every single one of those graphs is slightly different, okay? How it works is if you have an odd number power for your multiplicity, so like 1, 3, 5, 7, that kind of thing. So like in this case, since there's no power there, those would both lead to like the power of 1. At those spots, it's going to cross the x-axis and it's going to go past it. So like at -6, it would go past it, and at 7, it would go past it. If your multiplicity is an even number, so like here at the 6, it's an odd, and at the 7, it'd be a positive 7 for the 0, it's even. What happens is it hits that spot, and then it bounces off the same direction. Okay, so you can see here at the -6 one, it's going to cross that line. At even ones, though, what it does is it comes down and hits that line, and it bounces off. Okay, so like in this situation here, both of these are even, so that's when we get like a W-shaped graph because it's hitting at the -6 and it's also hitting at the 7, but it's not crossing either of those because it's bouncing off. Okay, and that always happens when it's an even one. Again, is that life or death if you know that? No, but it kind of helps you understand why the graphs start getting crazy and why we actually care about this multiplicity stuff. Okay, but I'm not going to ask anything like that on the test. I just wanted to at least talk through it a little bit, but that's kind of why we're doing this stuff. So let's actually take a look at one of these examples then and hammer some stuff out here. Okay, so you have to flip back a couple pages on the wrong page here. Okay, 7-6. Okay, so what it wants us to do here is it wants us to find all of our zeros and their multiplicities. So they could be like regular numbers, they could also be our complex numbers with like our eyes for imaginary stuff, okay? What I would do first here is I would factor this out as far as I can go, okay? So when I'm factoring, my first thought is there a greatest common factor that I can pull out of all of this stuff, okay? So like looking at all of these things, is there something I could divide every single one of those terms by to kind of get rid of it? Okay, that's my first thought. So there, if they all have powers of t or t to the power of something, can I pull some t's out front? Yeah, so that would be my first thought. So what I would do here is I would take this, I'm just going to rewrite it down here, f of t is equal to 9 t to the 15th minus 6 t to the 14th plus t to the 13th. And my goal is to pull out as much as I possibly can. So since the biggest one there's 15, smallest one's 13, I know I've got at least 13 t's in each of those. So I'm going to pull that t to the 13th out front. So what I'm going to do is I'm going to rewrite this as pulling a t to the 13th out front. If I pull 13 t's out of like t to the 15th, that would leave me with 2 left. So that would be like 9 t to the 2nd. If I pull 13 t's out of t to the 14th, that would leave me with 1 t. So it would be like minus 6t. And then if I pull 13 t's out of 13t, be careful here, you can't write it as 0. You have to write it as 1. Because if we went back and did the distributive property out there to like unfactor it, if we took t to the 13th times 0, then it wouldn't show up here. So if you pull all of it out, you still have to leave a 1 there. Okay, follow me so far? So then now my goal here is to find what the zeros are. So I'm going to take this and I'm going to set it equal to 0. Okay. We have one chunk here that's already good to go and is factored as far as we can. So we're good to go with the t to the 13th. We could set that up right away and find what its 0 is. This, though, we can take and we can factor further. Okay, so this is going to kind of mix in the stuff that we were doing the other day, where we were doing like the quadratic formula to do the factoring. You remember that before break we did? So I'm just going to draw a line here so we know it's kind of a separate thing. We're going to use quadratic formula to factor out this back part here. So basically, you remember from quadratic formula, we come up with our A, our B, and our C. Our A is going to be 9. B is going to be negative 6. And then C would be 1. And again, we're getting that stuff from this back part here. We're factoring that stuff out. That's where that's coming from. Okay, and then we do our quadratic formula. So that's the, in this case, t technically instead of x, but if you put an x, I don't really care. So t is equal to always the opposite of b, so positive 6, plus or minus square root of our b squared, so negative 6 squared. Make sure when it's a negative you put it in parentheses if you're using your calculator. Minus 4 times our a, which is 9, times our c, which is 1, over 2 times our a value, which is 9. Then we just simplify her out there, so we'd have 6 plus or minus, under our square root, negative 6 squared is 36, minus 4 times 9 is 36, times 1 is 36, over, and then 2 times 9 is 18. This one is going to work out where when we subtract this, we're going to get 0, so it'll be like 6 plus or minus, technically square root of 0, which we know is just 0, over 18, and we could write it as that 6 plus or minus 0 over 18. So now this is going to be a situation kind of like what we had in the packets that I was kind of showing you with the multiplicity business, because here if I add 0 or subtract 0, is that going to change my answer at all, or am I going to have one answer? One answer, right? I'm still going to show you in 2 separate ways here. So one would be like where I add 0, one would be subtract. Either way though, I'm going to get 6 out of 18, which would reduce down to like a third. So what that means is my t value is a third, so that would be like one of my zeros, right? But it's going to have a multiplicity of 2 because I got that twice, okay? So how this works, like if I was rewriting this as a factored form here, we know whatever our 0 is, when we put it in our parentheses groups, we always do the opposite because it would be like, 1/3 minus 1/3 to get 0, so it would be like t minus 1/3, and then also t minus 1/3, and then I'm going to drop down my t to the 13th. But we know there, this and this are exactly the same. So that's the same as like t minus 1/3 squared. And then our t to the 13th there. So then when we do this out for like our zeros, like I said here, since this happens twice, this is one of our zeros, but it's a multiplicity of 2. So you just write it like that. So like t is equal to 1/3 with a multiplicity of 2, and again, if it was already pre-factored out for us like this, you could just look at the power to get that, and then you know it's a positive 1/3 because 1/3 minus 1/3 is going to give us 0. And then our other answer there is from this other part of it, so like that's part of it, and that's part of it, because we also have a t value at 0, because if I take 0 to the 13th, doesn't that kick me out of 0? Should, right? So my other value there is t is equal to 0, and the multiplicity on that, even though we didn't do any solving there, is 13 because that's what the power is. So t is equal to 0 with multiplicity of 13. Relatively-ish makes sense? Okay. I'm going to show you one more thing while we're here. You don't have to write this, but I kind of want to show you. So, I'm just going to kind of do it down here. If we have a situation where this doesn't come out to be 0, so like say we had like 6 plus or minus, and say under our square root it was like 81 or something like that, over 18, in this case you will actually have multiple answers, and they'll both have a multiplicity of 1. So like here, if we did square root of 18, we know that's 9, so like 6 plus or minus 9 over 18. So then there, when you go to do your breaking, you'd have one that's like 15 over 18, and then you'd have another one that would be, what would that be, negative 3 over 18, or you could reduce those, would that be, it'd be 5 over 6, and negative 1/6. So in this case, you would have separate ones factored out here. So like you'd have one that would be like t minus 5 over 6, and t, it would be plus because that's a negative. But both of these would have multiplicities of 1 because they're different numbers. Okay, does that kind of make sense? So if it's the same number, multiplicity of 2, because it would be like a power of 2. I know there's going to be some that like are on the, assignments and stuff that are like that where it does come out separate answers. If it's separate answers like that, they just have multiplicities of 1. Another thing to note here is the number of multiplicities should always add to your highest degree. So like here, our highest degree was 15, 13 and 2 adds to 15. Okay, if it was like something like this and it came out like this, it'd be 13 plus 1 and 1, which also adds to 15. Is that relatively-ish? Make sense? Okay. All right. Next thing here, polynomial graph wiggliness theorem. I don't know that that's a real name, but that's what they go with. So it says let p of x be a polynomial of degree n is greater than or equal to 1. So again, just a polynomial. Graph of p of x can cross any horizontal line y is equal to d at most n times. Okay, so what the wiggliness thing is graphs with higher powers are going to have more up and down spots. Okay, so we know like if it's just like a power 2, it's just the U shape. The more powers we get, like if it was that last one, power of 15 or whatever, that's going to have lots of up and down spots. Okay. It can have up to 15 up and down spots. It might not have that many, but it can have up to that many. Okay. Let's look at our next example then in our packets. So this is where they're going to use this wiggliness thing. So what they're getting at here is to figure out what the lowest possible degree is. What you do is it says like you can have some sort of horizontal line, y is equal to d. You are trying to basically come up with a horizontal line that crosses this curve-shaped graph in the most amount of spots. Okay, so like if I went and I made a horizontal line across there like that, that's going to cross our squiggly graph there in the most amount of spots. Then what you do is you just count up how many spots it actually crosses. So like here, you have 1, 2, 3, 4. So that would tell you that your least degree or the lowest degree that you could possibly have for this random polynomial would be 4. Okay, so your least degree would be 4. Okay. Now these technically wouldn't be the zeros because like in this case you'd have a 0 there and a 0 there, so those wouldn't be ones you worry about, but that's not what they care about. They just care about if you shot that horizontal line there, what's the most amount of spots you can hit. Okay. All right, and then one more thing to talk about here. So that conjugate zero theorem, so that's kind of like what we were talking about before. So it says let p of x equal blah, 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 and just lists out a polynomial there. And then it's just saying your power can't be 0. It says if you have a 0 or z that is equal to like a complex number, so like a plus bi, then the complex conjugate is also going to be an answer. And that's kind of what we put in our little packets here. That's what they were talking about here. If they told you this was a solution, this automatically has to be a solution. Okay, so if they just gave you that and said, hey, what's another spot it crosses? That one has to be it because complex conjugates are always like, if one works, they both work, if that makes sense. Okay. All right, now let's tack our last one here. Okay, this one is the crazy one, so bear with me. All right, so we are given that negative 1 is one of the zeros of our function there, g of x. And then we're supposed to find all of the other zeros that we could possibly have, okay? So if they tell us that -1 is one of our zeros, that would mean that like x plus 1 would have to be one of our factors. So whatever they say your zero is, that tells you that that has to be one of the factors, or one thing that would be, you know, things we multiply to get this total number, okay? So what we can do is, if we know one of the factors or know one of the zeros, we can use that long division stuff we were working on the other day to kick out what the other factors would be, okay? So what I'm going to do here is I'm going to take this and I'm going to do my long division out. So I'm going to do, I'll do it right here. I know x plus 1 is a factor, so that's what I'm going to divide by. Then under my long division sign there, I'm going to write this whole thing out. So it would be like 4x to the third plus 6x squared plus 5x plus 3. Then I do my same long division I was doing the other day. So basically I'm looking, okay, what do I have to take times x to get 4x to the third? So that would be like 4x squared. And I always just do it off to the side so I remember, and 4x squared would go up as part of our answer. And you're always taking that times what you were dividing by here. So that'd be the same as like 4x to the third plus 4x squared. And then remembering from the other day, that's what we're subtracting by over here. So we would subtract, and you want to make sure that you're subtracting by this whole chunk. So I always put it in parentheses. So it would be like subtracting by 4x to the third plus 4x squared. Then the thing people mess up on here is they forget that we're subtracting by everything. So when I do it, what I do is I switch this from subtracting to adding the opposite on each of those. That way I don't forget that I'm subtracting that back one, okay? Says then what should always happen is these first ones should always cancel out because we chose a number to make it cancel. Your stuff should line up here, so x squared and x squared, so like 6 minus 4 would be 2. So 2x squared. Then whatever your remaining thing is, you can just drop that down. So you can just drop down, I'm just going to drop down to 5x for now and then worry about the 3 in a bit. So I just do the same thing. I'm looking, okay, what would I take times x to get me 2x squared? Well, that would be 2x. So it would be 2x times x plus 1. 2x would go up as part of my answer. And then this would give me 2x squared plus 2x. Again, that's what I'm taking over there and subtracting by. So minus the 2x squared plus 2x. And again, you're subtracting by both of those, so switch it to add the opposite on both. First thing should always cancel. 5 minus 2 would be 3x. And then drop down that plus 3. And then we'll have, to get what we need, we'll have to take it times 3. So plus 3 would go up as part of our answer. And then that would be 3x plus 3, which conveniently works out for us, right? Because that's what we needed there. Because then when we go to subtract, gone, left with 0, and you shouldn't have any remainders with these ones. So then what that does for us is that tells us that this function here, so I'll draw a line here, g of x is equal to 4x to the third plus 6x squared plus 5x plus 3 is the same as us factoring out that x plus 1, because we knew that from the beginning, they told us that, times, and then whatever we got for our long division thing, because it's like undoing our multiplication. So 4x squared plus 2x plus 3. But the sucky thing here is this can also be factored for its cubed. Okay, we'll keep going tomorrow.